Qwen4's architecture is already here, Qwen3.8 Flash Next explained. Qwen just did something much more interesting than releasing another model. They released Qwen3.8 Flash Next, and according to Qwen themselves, this is an early preview of the architecture that will be used for Qwen4. So while Qwen4 itself is not released yet, we now have our first serious look at what is happening inside it. And Qwen is changing much more than just the attention mechanism. They changed attention. They changed the residual connections. They introduced a massive new type of memory through engram embeddings. They changed how the model is trained. And they are combining all of this with an extremely sparse mixture of experts architecture. So let's break down what Qwen4 is actually becoming. First, this is not just Qwen3.8 with more parameters. The previous Qwen generations already moved away from the classic transformer architecture. Qwen3 next introduced a hybrid design where most layers used gated DeltaNet, while occasional layers still used normal global attention. That architecture eventually became the foundation for Qwen3.5, Qwen3.6, Qwen3.7 and Qwen3.8. Now Alibaba is doing the same thing again. Qwen3.8 Flash Next is effectively their experimental platform for the next architecture. And this time the major changes are gated DeltaNet plus Qwen Sparse attention, gated residual, engram embeddings, ultra-sparse mixture of experts, multi-token prediction, and a new training recipe based around the Muon optimizer. Let's start with attention. This is probably the biggest architectural change. Qwen is still keeping gated DeltaNet, or GDN. Instead of every layer performing expensive transformer attention across the entire context, gated DeltaNet maintains a compressed state representing previous information. Think of it almost like a continuously updated memory. You don't have to keep searching through everything you have ever read just to remember the general state of the conversation. But compressed memory has a weakness. Sometimes the model needs one exact piece of information from much earlier in the context. And that's where attention comes back. The architecture follows this pattern. GDN, 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 then an attention layer, and repeat. So 3/4 of the sequence layers use gated DeltaNet, while 1/4 perform global retrieval. Qwen3.8 Flash Next contains 48 layers, meaning 36 GDN layers and 12 global retrieval layers. But those global layers aren't normal attention anymore. Qwen created something called Qwen Sparse attention, QSA. And this is probably one of the technologies that will matter most for Qwen4. Qwen Sparse attention. Traditional attention basically asks, which tokens in my entire context are important? With a 1,000,000 token context, that's a massive search space. Other sparse attention systems tried to solve this by first finding important individual tokens. But Qwen argues that even the indexer searching those tokens becomes expensive when context gets extremely large. So QSA does something different. It divides the context into tiny microblocks. Instead of initially evaluating every individual token, a lightweight indexer evaluates those blocks. It first asks, which regions of this enormous context are probably relevant? And only after finding those regions does the actual attention mechanism retrieve the precise information inside them. So essentially, GDN handles compressed memory. QSA handles precise retrieval. And we actually know the implementation in surprising detail. The current architecture compresses groups of 4 tokens for the index. The QSA indexer then selects up to 512 blocks, which expands back into roughly 2,048 token positions for actual sparse attention. The attention component itself uses 24 query heads and only 2 KV heads, while the lightweight indexer uses 4 query heads and 1 shared key head. And importantly, each QSA layer performs its own selection instead of simply sharing the same sparse attention map across the entire network. That last part matters. Different depths of the network might need completely different information. An early layer might care about syntax. A later layer might care about some piece of code from 400,000 tokens ago. Qwen lets each attention layer decide independently what information it needs. And then Qwen changed something even more fundamental: the residual stream. Normal transformers basically have one main residual stream. Every layer reads from it, processes something, writes information back into it. Then the next layer does the same thing. After dozens or hundreds of layers, information from early in the network can become increasingly mixed together. Qwen's new solution is called gated residual. Instead of one residual stream, Qwen3.8 Flash Next has 4 parallel residual branches. Imagine replacing one highway with 4 highways. Each layer can dynamically decide: which highway should I read information from? How much information should I take? And which highways should I write the result back into? The read operation uses a data-dependent element-wise gate, while writes are controlled per branch. Qwen says something particularly interesting appeared during their experiments. One of these residual branches naturally developed into something similar to a long-range information highway, carrying information from an early attention layer through much of the rest of the network. That's fascinating because it means the network isn't just becoming deeper. It now has multiple ways for information to travel through depth. Qwen also designed these residual states so they can be stored in FP8, reducing memory traffic. And the gated residual implementation in this model uses 4 branches with a low-rank bottleneck. But the strangest part might be the n-gram embedding. This is where Qwen4 starts getting really interesting. Normally, when an LLM receives a token, it performs an embedding lookup for that individual token. Qwen now adds another memory system. Instead of only looking at one token, the model can use combinations of nearby tokens, n-grams, to retrieve additional learned representations. So common combinations of words, code patterns, and local structures can effectively have their own learned memory. In Qwen3.8 Flash Next, this is enormous. The transformer/Mo backbone contains around 125 billion parameters. Then Qwen adds another 51 billion parameters just for n-gram embeddings. And there is also an additional MTP component. Yet only around 6 billion parameters are activated for each token in the main model. This is a completely different way of thinking about scaling. Instead of saying, "We need every new parameter to participate in expensive matrix multiplication," Qwen is saying, "What if billions of parameters behave more like an enormous lookup memory?" And because the model knows which n-gram embedding it needs ahead of time, Qwen says this giant table can actually live in CPU host memory. The required entries can then be asynchronously prefetched while the GPU is doing other computation. So those extra parameters don't necessarily have to permanently consume accelerator memory. That's a very big idea for future local models. Model intelligence may increasingly come from different classes of parameters. Parameters that require computation. Parameters inside experts that are only conditionally activated. And giant memory-like embedding tables that can potentially sit outside the GPU. The Mo is still insanely sparse. Qwen isn't abandoning mixture of experts. It's pushing sparsity even further. Qwen3.8 Flash Next has 512 experts. For each token, the router selects 10 routed experts, plus 1 shared expert. Each routed expert has a relatively small intermediate dimension. This is important because Qwen has essentially separated model capacity from compute per token. You can have a very large expert pool, a huge n-gram memory, a large overall parameter count, while only touching a small fraction of the network for each generated token. That philosophy looks central to Qwen4. There is another piece, multi-token prediction. Qwen is also keeping MTP, multi-token prediction. Instead of training the network only around predicting the immediate next token, the additional prediction module is trained across multiple future steps. This serves two purposes. It can improve the backbone during training, and during inference it can act as the draft component for speculative decoding, allowing several possible future tokens to be proposed and verified together. Qwen has even replaced the MTP module's normal full attention layers with the new QSA mechanism. The serving implementations are going further. SGLang has already implemented a system where MTP can reuse QSA indexing information across speculative decoding draft steps instead of repeatedly searching the long context. That gives us a good indication of how aggressively this architecture is being designed around real-world inference rather than just training benchmarks. Qwen also changed how these models are trained. Qwen3.8 Flash Next is trained primarily using the Muon optimizer. But they don't use Muon on everything. The large two-dimensional linear transformations, attention matrices, gated DeltaNet projections, and low expert weights use Muon. But things such as embeddings, the Mo router, and low-rank gated residual parameters continue using AtomW. Even fused matrices are treated carefully. If QKV or other transformations are fused together during implementation, Qwen separates the logically independent transformations before performing Muon's orthogonalization. They also refitted their scaling laws specifically for this architecture. And interestingly, Qwen says traditional batch size warm-up was unnecessary for this training setup. They can begin training directly at the target batch size while using larger learning rates. So Qwen4 isn't just a new inference architecture. The training recipe itself is changing with it. There are also several smaller architectural details worth watching. Qwen retains zero-centered RMS norm. It keeps attention output gating. It uses normalized initialization for the Mo router. And the model uses partial rotary positional encoding rather than applying rope across every dimension. The current model also has a hidden dimension of 2560 and a vocabulary padded to 248,320 entries. Again, these exact numbers belong to Qwen3.8 Flash Next, not necessarily the final Qwen4 models. And yes, it is multimodal. This isn't purely a text architecture. Qwen3.8 Flash Next includes a vision encoder. The released configuration shows a 27-layer vision network, hidden size 1152, 16 attention heads, and an output projected into the language model's 2560 dimensional hidden space. It processes spatial image patches as well as temporal patches for video. So the architectural preview we are seeing for Qwen4 is already being developed as a multimodal system rather than having vision simply bolted onto a finished text model later. So what does the full architecture look like? For this Qwen3.8 Flash Next implementation, imagine this. Tokens enter the model. You have normal token embeddings plus a giant n-gram lookup memory near the beginning. Then the network enters the main stack. 3 gated DeltaNet layers, each followed by mixture of experts. Then 1 Qwen sparse attention layer followed by mixture of experts. That 4-layer pattern repeats 12 times. Running across all of those layers aren't 1 but 4 gated residual streams. On top of this is the multi-token prediction system for speculative decoding. And visual information enters through its own vision encoder before being mapped into the language model representation. The structure is essentially n-gram memory, GDN, Mo, GDN, Mo, GDN, Mo, QSA, Mo. Repeat. With gated residual pathways running across the entire network. And this tells us something important about Qwen4. The most interesting thing isn't one individual feature. It's the direction. LLMs are slowly moving away from the idea that everything should be one enormous standard transformer. Qwen is separating the problem into specialized systems. Gated DeltaNet acts as compressed memory. Qwen sparse attention becomes selective retrieval. N-gram embeddings provide enormous cheap lookup capacity. Mixture of experts provides conditional computational capacity. Gated residual gives information multiple routes through the depth of the network. And MTP turns extra prediction capability into faster generation. This is becoming less like one gigantic neural network doing everything in the same way, and more like several specialized memory and compute systems working together. But one warning. Don't take the specifications of Qwen3.8 Flash Next and assume Qwen4 will simply be this model with a new name. Qwen describes this as an early architectural preview, and says the design will continue being refined toward Qwen4. So we do not yet know the final Qwen4 model sizes, number of experts, active parameter counts, number of layers, or exact context configuration. But the architecture itself? We finally have a very good idea of where Qwen is going. And if Qwen3 Next was any indication, because that architecture eventually spread across Qwen3.5 through Qwen3.8, then what we're looking at today could become the foundation of the entire Qwen4 family. And that makes Qwen3.8 Flash Next much more important than its name makes it sound. This may basically be our first look inside Qwen4. That's it for the video. If it helped, please give it a thumbs up. Thank you for watching and see you next time.